Hello and welcome to another Java tutorial. In this tutorial, I'm going to continue our discussion on calculating Bessel functions. And in the past lectures, we discussed how to calculate the Bessel function of the first kind for a small arguments, large arguments, and then we discussed the Bessel function of the second kind, which is also called Newman function or Weber function. And then we said that these are the solutions of the Bessel differential equation, and y nu is basically defined based on j nu and j minus nu. And the reason we do this kind of definition is because j nu and j minus nu are always solutions to the Bessel differential equations, but they are not necessarily linearly independent. And in order to be able to write down the general solution of a second order differential equation, we need to have two linearly independent functions. That's why we do this definition for the Bessel functions. For non-integer values, for the parameter nu, j nu and j minus nu are indeed linearly independent, so we don't need to use yn or define yn. But because for integer values j nu and j minus nu are not linearly independent, we have to define this y nu, and we always take j nu and y nu as two linearly independent solutions for the Bessel differential equations. And then we said that one interesting property of these Bessel functions, j nu and y nu, is that they represent the amplitude and the phase, and that's what we actually discussed during the trying to come up with a polynomial expansion for the large arguments. And we said that j nu resembles some amplitude cosine of some phase, and y nu some amplitude sine of some phase. And because the amplitude is common, if we combine these by the imaginary number j, then j nu plus j y nu is just some amplitude e to the j some phase. So Hankel 1 and Hankel 2 are defined such that they resemble propagating waves, right? Not standing waves, propagating waves. And we said that Hankel 1 actually represents the solutions of the Bessel differential equation in a cylindrical coordinate system. These are the wave solutions. And then Hankel 1 resembles an inward propagating wave, a wave that is propagating towards the center of the cylinder. And Hankel 2 is a wave that actually moving away from the center, so it's an outward propagating cylindrical wave, right? And we said that Hankel 1 and Hankel 2 are by definition complex numbers, so we have to implement them with the assumption that the return type of the function is always complex numbers. But then Bessel functions, it turns out they have a very interesting property, and that is that there is some recurrence formula, and these are exact formula. And by recurrence we mean that j nu is somehow related to other j parameters such as j nu minus 1 and j nu plus 1. Now what turns out to be very interesting is that j prime nu, so the derivative of the Bessel function, can be written as the combination of two different Bessel functions. And again, this is an exact relation. What I mean is that, typically if I want to calculate j prime nu at some x, I have to calculate j nu at x plus h minus j nu at x divided by h when h goes to 0, right? I have to have two evaluations of j nu at two very close points and then let the h go to 0, right? But that always gives me an approximation for the derivative j prime nu. This relation tells me that j prime nu is 1/2 of j nu minus 1 minus j nu plus 1, and this is exact. And I already know how to calculate j nu minus 1 and j nu plus 1, right? We spent quite some time developing a very efficient way of calculating Bessel function j. And the other interesting recurrence formula relates j nu to j nu minus 1 and j nu plus 1. So this is the value of j nu. The next one is j nu prime. And here it says that j nu minus 1 plus j nu plus 1 is 2 nu over x j nu of x. And if we change plus to minus, we end up with derivative 2 j nu prime of x, all right? And we can just rearrange these equations and turn them into these equations. X j nu prime plus nu j nu is x j nu minus 1. Okay, so multiply by x here in both sides, and then replace for use the other equation to come up with these equations. And then x j nu prime minus nu j nu is minus x j nu plus 1, right? And again, the point here is that we can exactly calculate the derivative of the Bessel functions, because it's just evaluating two Bessel functions at nu minus 1 and nu plus 1 and taking the difference, right? Now, because y nu was defined based on j nu, so these relations also are valid for y nu. We can show that. So in particular, y nu prime is 1/2 y nu minus 1 minus y nu plus 1, all right? And then because Hankel functions were also a linear combination of y nu and j nu, these relations are also correct for Hankel functions. So the derivative of Hankel function 1 over 2 is 1/2 Hankel 1 over 2 nu minus 1 minus Hankel 1 over 2 nu plus 1, all right? So here's an example. I'm plotting j0 of x from 0 to 100, and then I'm also plotting the j0 prime, which means the derivative of the Bessel function, with red. And as you expect, whenever j0 reaches its peaks, j0 prime crosses the horizontal axis, the 0 axis, all right? And what's very interesting is that when the x gets very large, we see that the j0 and j0 prime are in sync. What I mean by that is that if j0 behaves like a sine function, j0 prime behaves like a cosine function, and the sine and cosine are in sync, which means that whenever sine becomes maximum, cosine becomes 0. Whenever sine becomes 0, cosine becomes maximum, plus or minus, right? And we can exactly see that in these relations. So let's head to Eclipse and try to do this plot. So in Eclipse, to refresh your mind, we have this Bessel function. So we implemented two ways. One was Bessel function integration. We're just using the integral definitions, which is very slow. And the other one is based on polynomials. We have one polynomial expansion for small arguments and one polynomial expansion for large arguments. And then we combine them to calculate j nu. And we can extend them to also to complex numbers, okay? And then here in the test j nu. So now what I'm doing in the Bessel function, I have added these j nu derivatives. So j nu deriv is just j nu prime of x, and it's just 1/2 or 0.5 times j nu at nu minus 1 minus j nu at nu plus 1. So it's important to write minus here, all right? And it again works for complex numbers too, because j nu, we implemented it for both real and complex numbers. So the next one is also j nu prime of x for complex numbers. Y nu deriv, this is the derivative of the Newman function, y nu prime of x. The next one is also calculating the Newman function for complex x. And then the next one is the Hankel function, the derivative of the Hankel function. So Hankel nu and order 1 prime of x. And the last one is Hankel 2. So Hankel nu of order 2 or second kind of x with a prime here to show that it's the derivative, okay? So these are the derivatives, and we can go to basically try to plot them. So I have created this test class. So in test 1, I'm creating our Bessel object, and then from 1 to 100. So actually let's set it to 0. I want to plot j0 and j0 prime, right? j nu deriv is the derivative of the j0. And in the PowerPoint, I'm going from 0 to 100. So let's keep it from 0 to 100 with 1000 points. I'm setting up my timer, and Oh, by the way, about this timer, so I'm using this timer from my MathLib class, which you can just download from GitHub. So it's in the util, this timer, and it's very simple. It has a start time, end time, and elapsed time. So when you start it, so when you create the timer, so they all start from 0. When you start it, it calls the system and current time millisecond. So the time is in millisecond. When you stop it, it gets the time from the system again and then calculates the elapsed time. When you reset it, it sets them to 0. When you call the show method, it just prints the elapsed time. The toString method is basically the same as the show method. So instead of doing this, I could just call the show method. All right. And then there is another timer. So if you don't want to use this, there's another timer which is very similar, and I believe it's in, if you go to the reference libraries, and these are all the math libraries available out there for Java, which I have gathered here. In the colt library, there is this cern, and in the cern, I believe there should be a time. So in the colt, cern colt timer, and this is very similar to what the timer that I have written. So it's a timer. It has a base time, elapsed time, and then it has when you create a timer, it just resets it for no particular reason. We already know that the long variables already initialized to 0 anyways, and then when it calls display, it just prints out this. So it calls the toString method. And then it has elapsed time. It calls another method seconds, and it takes the millis, and millis is just current time minus base time, and the base time is just the originally 0, and then minus, and then minutes, it takes the seconds, divide them by 60, and then plus, it has reset. So it's very similar to mine. It has a start and a stop. So it's very easy to write a timer class so that you can time your code. Obviously, it's not a very accurate way of timing your Java code, but that's one way to get a feeling of how fast your code is running. And you can just use this one in the colt library, or just use the one in my source folder in the utils. I have this timer. All right. So back to our Java. Back to our Bessel function. So we are plotting J0 and J0 prime, and then I'm also plotting a line that crosses the 0. So let's run this. 16 milliseconds, pretty fast. And let's see. So blue is J0 and red is J0 prime. Now we know that the J0 here is horizontal, so the derivative is 0. That's why the derivative starts from 0. And then the derivative, the slope is negative, obviously, until we get to here. So whenever Bessel is at one of the peaks, here, minimum, maximum, the derivative crosses 0, right? At this point, the derivative is 0, which means the Bessel function is at maximum. Again, this point, all right? Now, as you can see, basically, when we look at the large values, we see that the peak is at 0, but the 0 is also at the peak of the derivative, and this is very similar behavior to sine and cosine functions. Now, if you look at the beginnings for small arguments, obviously the peak should be at the 0 of the derivative, but the 0 is not at the peak, is slightly offsetted. So the 0 is not exactly at peak. So at the beginning, the Bessel function is not exactly behaving like a sinusoidal function. But when x gets large, we see that whenever the Bessel function is at maximum or minimum, the derivative should be 0. That's the fundamental theorem of calculus. But whenever Bessel function is crossing 0, the derivative is almost exactly at the peak. So the Bessel function is behaving very similarly to a sinusoidal function. And obviously we know that the amplitude should drop very slowly. So the amplitude is not constant anyways. You see there is a very slow drop in amplitude. But locally around here, for example, in this interval, the Bessel function J0 is very similar to a sinusoidal. And a similar thing for the so just one last thing about the Bessel function. When I run these, I can export them also and compare them to the results in Python, because the Python library, the scipy.special package, it also implements the derivatives of the Bessel function, and it makes sense because it's a very simple equation. And so let's go to our Jupyter notebook here. I already have a NumPy, matplotlib, and scipy.special. These are our values. So x0, y0 is j0, x1, y1 is j0 prime. So plt plot x0, y0 and color B, and then label Java, and then plt x0 scipy.special j new, and we want to calculate 0 and x0 color red and line style dash, and then this is Python. So we get the perfect fit. And then we can also plot the derivatives. So instead of y0, I put y1. And here, instead of j new in the scipy.special, we have j new p. Okay? J new p is j new prime. In the Java code, I wrote j new deriv, but here we have j new prime. Compute nth derivative of Bessel function j new of z with respect to z. So 0 and x0. So we're calculating the derivatives, and as you can see, there is a perfect fit. All right. So we calculate the derivative of Bessel functions not by numerical approximation, but by the exact relations from this recurrence formula. J nu prime is 1/2 j nu minus 1 minus j nu plus 1. All right. Okay. So you might be asking, okay, we spent all this time and developing a very efficient Java code for calculating Bessel functions. So what are the other libraries out there for Java that calculate the Bessel functions? And here's two famous examples. One is from the colt library, cern.jet.math.bessel. So there is a Bessel class there, and it's a very limited implementation. I believe it only calculates for integer parameters, so jn. And none of these ever support complex numbers. For some reason, complex numbers were never standardized in Java. I don't know why, but these don't have implementations for complex numbers. And the next one I'm sure you're familiar with is Apache Commons Math. And I believe it's version 3.6.1 that I'm using. So in the Commons Math, if you go to org.apache.commons math3 in the special package, so they also have a package called special, and there's a Bessel J. So there is no Bessel K or something like that. It's Bessel J. And then these implement the Bessel functions or function calls or method calls using static methods. Remember, when I implemented that, I did not use a static implementation. So we have to create an object. So there is no static call. And the reason was because of calculation of the gamma function. And the fact that we are keeping a history. We're using the state of this Bessel object to keep a track of the history of the new values and the gamma values that have been calculated. Because as I mentioned, most of the time, we are not, the new is fixed. Let's say we want to calculate Bessel J0 or J1 at different x values. So we don't need to waste time calculating the gamma function over and over again. All right? Okay, so let's go back to the PowerPoint. So what I'm going to do, I'm going to compare the speed of these two implementation, Bessel from Colt and Bessel J from Apache Commons, with my implementation, and we're going to use the timer class that I just discussed to time them. I've already done one test, and my implementation was about 15 milliseconds for 1000 evaluations. The colt library took about 52 milliseconds, so a factor of 4, 3 or 4 slower. And the Apache Commons one took 77 milliseconds, which is a factor of 6, a factor of 5 slower. So my implementation seems to be the fastest. And again, we are going to look at the source code for these two, and these are implemented in a very long way. They have like hundreds of lines of code to implement the one Bessel function. And my implementation, if we go back and look at the, for example, new, we separately implemented the Bessel function for a small argument and large argument, and each one takes about 10 lines of code. And the reason here is that I'm using the power of sequences. The way we implemented the sequences as a functional interface, and then we take advantage of the lambda notation. If you are not familiar with my lectures on sequences and series, definitely go check them out. It's very valuable for you to know the fundamental concepts of sequences and series, because all of the calculus is based on the sequences and series. The limit of a function is just a sequence that eventually converges to a value, right? So the calculus is based on sequences and series. Integration is based on limiting this, calculating the value of the infinite sum, which is a series. All right, so what I want to do, I want to write these tests, and before that, let's just recap about these libraries. The problems that these two have, at least my opinion, they're a slower implementation. They have no support for complex numbers. So if you want to calculate Bessel functions, any of them for a complex number, these libraries don't have support. They are mostly implemented for integer n, so generally they don't support double nu, right? And one of the reasons was that for Bessel functions, when we are evaluating at for double nu and double x, when nu is a non-integer and x is negative, the result is not even a real number, it becomes a complex number. So that's why we have this warning that pass x as a complex number, so that we can invoke the other nu that calls complex numbers, and this has no problem returning the complex value. All right, so that's one reason that they don't have usually support for double nu, because it requires to take care also of the complex numbers that it might return. And they generally don't have support for Hankel functions, because Hankel functions are by definitions complex numbers. So if they don't support complex numbers, then they cannot support Hankel functions. All right, so let's head to Eclipse and try to write this test and compare the speeds of all these three implementations. So I'm going in the test package here, I'm going to create a class called test new speed. All right, so here we're going to have three tests: test 1, test 2, and test 3. All right, and I'm going to start from test 1, which is the implementation that I taught in this lecture. So this is from my library, my implementation, or let's call it my implementation. Test 2 is going to be a colt library, and test 3 is going to be Apache Commons math library. All right, so let's start with the first one, public static void test1. And in test 1 we're going to create our Bessel function, which comes from our library Bessel, and it's a object, so we have to instantiate it. We're not invoking any static method. Bessel function. All right, and don't forget the keyword new. And then we create our array. Double x is math utils, linear space from 0 to 100, 1000. All right, and then double j0 is array func dot apply t goes to Bessel dot jnew, and we're going to set 0, t, and x, and we're going to calculate j0, j1, j2, j3, j4, or maybe let's just go with j3, j0, j1, j2, j3. all right, and let's also plot them just for the fun of it. MATLAB chart, fig, new MATLAB chart, fig.plot x j0 to with color b 2f j0, and then j1, j2, j3, j1, j2, j3, red, green, and black. j1, j2, j3, and then we're going to fig.render plot, fig.legend on, and fig.show with the exit flag. all right, and obviously I want to time it, so timer, new timer. all right, let's just import the timer. So you can either use my library or from the cern.colt. so I'm going to use the timer from my library, so timer.start, and then we calculate the Bessel functions, timer.stop and timer.show. all right, everything is ready. Let's run this. 11 milliseconds, and I have to go to run arguments, remove this so that I can see the plot. 9 milliseconds, and I forgot to change the index here. 18 milliseconds. all right, so 18 milliseconds for my implementation, and the next one is test2, public static void test2. all right, and we have basically the same code here, the same timer, but then here instead of calling Bessel, I'm going to call Bessel, and this Bessel comes from cern.jet.math. all right, and it's a static invocation. What you notice that it doesn't have a jnew method, so it has a jn method, so it only has implementation for integer numbers, not the double numbers. That's one of the limitation. all right, Bessel jn, it doesn't have a jnew, it doesn't support double new parameters, only integer parameters. Let's just jn1, jn2, and jn3, and notice that because these are implemented as static methods, there is no state of the object for here, so it doesn't keep track of the history that has been calculated. That was actually one of the tricks that I used to speed up the evaluation process. So we're going to go to test2, which is the colt library, cern library. So let's run this. So my implementation was 18 milliseconds. Let's see how fast it takes. 55 milliseconds. So again, the plots are pretty much the same, right? But then the time from 18 to 55, it's a factor of 3-4 difference. all right, now the last one is Apache Commons one. So public static void test3, and the code is pretty much going to be exactly the same, but then here we are going to use the Bessel j from the Apache. So Bessel j, and we're going to import it from org.apache commons.math3.special. And it has a method called value. Notice that it also is a static method, and the good news here is that it does implement double orders, not just the integer orders, so that's good. And then t, and we're going to copy, paste, and paste Bessel 1, Bessel 2, Bessel 3. all right, 85 milliseconds. So mine was 15 millisecond, 18 millisecond. The colt library was, I believe, 55 millisecond, and this one is 85 millisecond. And as you can see, we see that the implementation here is not as good as mine, and that's key. That's the very key. There are different ways of implementing the same thing, But remember, we are in the business of finding the most efficient way of calculating functions. That's very important, okay? All right, so one last thing that I want to check here is, let's call this test 4. Let's see what happens. So we saw that the colt doesn't support non-integer, but Apache does. So let's see what happens if the Bessel functions tries to become complex. So Bessel j dot value, if it's a non-integer order but then the x becomes negative, what happens? It returns an exception. Bessel function however cannot be computed for x equals minus 2.3. all right, and there was no support for passing it as a complex number so that we can evaluate it. Let me just import the j, import a static from complex. I'm going to use the complex from my library, complex. So, okay, I'm going to import all the statics, which also includes j. So it doesn't support for complex, so it cannot calculate because we already know that this becomes a complex number. So let's create it. Let's create from my library Bessel function, Bessel new Bessel function as sysout Bessel.jnew 0.5 minus 2.3. Let's see what happens here. All right, so let's remove this one. Throws an exception, which is not good. So it says that I cannot calculate it, and I'm returning that, but pass x as a complex number so that it can be correctly evaluated. So I cast it to a complex number, minus 2.3 plus 0j. Now we have no problem calculating it, and it becomes a complex number as we expect. But we are able to calculate because we support the complex numbers. All right. So I hope you enjoyed this lecture, and I'll see you in the next one.